Hi, thank you so much for joining us this afternoon. We're going to go ahead and get started in 3 minutes. Thank you so much for joining us this afternoon. We're going to go ahead and get started in 2 minutes. Thank you so much for joining us this afternoon. We're going to go ahead and get started in 1 minute.
Good afternoon, everybody. My name's Matt Newman, and I'm with the Cloud Security Alliance DC area chapter. And before we get started, just to give you a brief introduction, the Cloud Security Alliance is an international organization. We've got over 100,000 members focused on building security best practices for the cloud, and also to provide a source of communal expertise in cloud security. And I think as of now, we've got over 100 chapters and over 100,000 members. I do want to point out, though, that we are an all volunteer organization at the local level. So everybody involved with CSA-DC is a volunteer. And if you are interested in getting involved, please do reach out to us through our website, or feel free to shoot us an email. And today's webinar, Not All AI is Created Equal, is brought to us by Deep Instinct. And Deep Instinct basically uses deep learning AI to create an artificial neural network that can identify attacks in just milliseconds, and doing so with the highest rate of detections and minimal false positives. An interesting note is that organizations that have adopted Deep Instinct cybersecurity products frequently don't even know that they've been targeted. And so our speaker today is Brian Black. Brian is a cybersecurity and intelligence expert leading Deep Instinct security engineering team, overseeing North and South America. He's a thought leader and a technology evangelist with a wealth of knowledge on AI, deep learning, and machine learning. And in his off time, he's often found on the lecture circuit giving talks around online security and state-sponsored threat actors. Well, that is when he's not phishing or competing in an online CTF hacking competition. So with that, I'll turn it over to Brian.
Awesome, thank you very much. So give me just one moment to share my presentation here. So the topic today is not all AI is created equal. And a lot of times this is billed as machine learning versus deep learning. And that's kind of a narrative I'd like to move away from, if you will. It's really machine learning and deep learning. They are, I don't want to say necessarily two sides of the same coin, but at the same time, they are nested within one another. Deep learning is an algorithmic subset of machine learning, as you're going to see in a moment. So we're going to talk about the pros and cons of each and how they are being utilized in today's world to solve all kinds of problems. So to start, we're going to begin with a bit of a history lesson. We talk a lot about artificial intelligence, and really you can't turn on the TV or browse the web without seeing some type of technology powered by AI. It's kind of ubiquitous and it's everywhere. But we have to start thinking about what AI means. I'm fairly certain the other day I bought a toaster that was powered by AI. So we really kind of have to narrow down what that means. So artificial intelligence really came about with the dawn of computer science in the 1950s. Many people will argue the 1940s. I will raise my hand. I'm one of those people. And really, artificial intelligence has a very simple definition. Can a computer do something on its own independent of a human? A lot of things are AI by that definition, including when we start talking about the world of cybersecurity, signature-based systems. They have their signatures and they're monitoring the network or the endpoint all the time, real time, matching those signatures, and they're doing it without human interference. But I'm not entirely sure anyone on this webinar or anyone in general would call your signature-based systems from the 80s or 90s to be advanced AI. So around the 1980s, though, we saw the rise of machine learning. Now, machine learning, quite frankly, is awesome. It has allowed us to do an incredible number of things with computers that were never possible before this algorithmic set existed. The first and foremost is we could perform feature extraction. That is, we could explain to a computer what a thing was. And that thing could be anything. It could be images, speech, binaries. It could be all kinds of things. And once a machine learning algorithm had enough feature set, it could go out and it could find other iterations of that thing. So if you taught it the general principles behind what a dog or a cat was, it could go find other instances of dogs or cats. It allowed us to talk to computers for the first time. As I mentioned, they could make inferences. It also gave rise to some of the most advanced cybersecurity tools that we saw dominate the landscape for the past 20 years. But machine learning has challenges, and we're going to address those a little bit throughout the presentation. Around 2010, we saw the rise of deep learning. Now, I want to make note that while my company is called Deep Instinct, deep learning is not a marketing term. That is the name for the algorithmic set. And I don't want anyone to be confused when they hear neural networks and deep neural networks. Neural networks have been around forever. And quite frankly, that is how you train machine learning algorithms. Deep neural networks came about because of the introduction of multiple hidden layers. We'll talk about what hidden layers are in a little bit. Deep learning is a real revolution in how computers operate, because what data scientists did is they effectively sat down and they said, let's try and mimic the biological human brain. Let's try and figure out how humans learn and see if we can make a computer do the same thing. And that's really where deep learning came about and the algorithmic set behind it. So to do that, let's talk a little bit about how humans learn. So when you were very small, you didn't get a feature extracted model of what a dog or a cat was, right? Your parents, your teachers, or friends and family, they simply pointed to examples. They said, that's a dog, that's a cat. And your brain took in 100% of the information. And as you got more exposure and more repetition, you started to kind of build your own algorithms, your own biological algorithms as to what comprised a dog and a cat. And eventually, identification of dogs, identification of cats became very simple for you, became trivial. In fact, I'm proud to say that right now, everyone on this call is a world-class leader in the identification of cats and dogs through your exposure and repetition. But you did something pretty remarkable when you were younger. And we don't really think about it. But at one point, you only had maybe, let's say 6 or 7, maybe 8 different types of dogs in your world. A German Shepherd, a Dalmatian, Labs. But you were walking down the street one day, you were very small, and a poodle crossed your path, or a Chihuahua. And you looked at it and you said, hey, that's a doggy. That's an incredible thing you did. You've never seen a poodle before. You've never seen a Chihuahua before, but you knew it was a dog. Now, you didn't know the name, Chihuahua, poodle, etc., but you knew you were dealing with a dog. That animal was effectively a 0-day dog to you. But through your previous training, exposure, and repetition, you were able to identify this brand new thing. This is also what allows you to drive on a daily basis. Every day, even taking the same route to work, you know, when we used to go into offices and whatnot, even taking the same route to work, while the path itself was the same, the conditions under which you drove that path were always changing. The background was different because you had different clouds in the sky, you had different colors to the leaves perhaps, or maybe you had snow depending on where you live. The cars around you were different. Your speed relative to them was different every single time. But yet, even though you were effectively exposed to this brand new scenario day in and day out, you had no problem navigating it. You arrived safely at your destination. And many times you did it while thinking about a bunch of other stuff. And you did that through exposure and repetition. Your ability to recognize that which is around you and make inferences, even from incomplete data, is what allows a human to be so successful at identifying dogs and cats, or even things like malware research. Humans are real good at that. It takes us time, a couple hours, maybe even a few days, but eventually we can identify any type of malware, even 0-day stuff. So that was the challenge that data scientists had when they started to say, how can we have a computer learn like a human can? So let's take a little trip down the path of how a data scientist arrives at the machine learning and deep learning models. What you're seeing on screen now is kind of for step one in a data scientist career. Can you write an algorithm to successfully identify the difference between a dog and a cat? That is really hard to do. And I'm willing to bet if I gave everyone on this call a pen and paper, it would take you hours. You may fill up multiple pages because of how challenging it can be. Because if you just think about their features, they're incredibly similar. They both have ears in the same place, eyes in the same place, nose in the same place. They've got 4 furry paws. They've got the tail in the same place. Now, there are exceptions to every rule, of course. But by and large, if you want to encapsulate the largest collection of animals, you write these features and you would find that they're incredibly similar between a dog and a cat. Now, there are some fundamental differences, right? For instance, the eyes of a cat and a dog are different. And that would work great. That's a good feature to home in on. The challenge there, of course, is that your model would break every time you came upon a sleeping animal. So that's kind of the first issue. Some people would say, well, cats have retractable claws. Very true. The problem is computers really struggle with zeros. They're great with ones, but they struggle with zeros. The absence of information to a computer is very hard for it to process. So when the claws are retracted, the data simply doesn't exist. There are no claws there to process. So while you can do it, it becomes challenging to make that a feature. And of course, when they're deployed, now you've got claws at the end of a paw, you got 4 furry paws. Once again, from a feature perspective, it looks just like a dog. So this is very challenging to do. Now, of course, data scientists by nature are very smart individuals and they can do it. But these algorithms are far larger than anything you could possibly anticipate. And they get down to the minutia. They get down to the ratios between the eyes and the ears, the distances between the tails and the front paw. And they start breaking out this ever increasingly complex series of algorithms to solve what seems to be a simple question. What is the difference between a cat and a dog? And that's really one of the challenges when we sit down and think about these simple challenges that to a human are trivial. To a human, we process that in milliseconds. And we can even do it when we don't have all of the data. One thing I always like to kind of comment to people is maybe you're at a party, you're in a house you've never been at before, you're sitting on the couch or sofa, and you look over, and from around the corner, you see an ear, maybe a nose and an eye, and a front paw. You have 5, 7, 10% of the data of what that animal is, but yet with a 99.9 and then a floating point of 9's confidence level, you can look over and say, hey, there's a dog over there. With very little data, and most of it obscured, you have an incredible accuracy rate. And you do that in milliseconds. That's, again, something that just the human brain excels at. In fact, identifying images when they are obscured or images within images is something just our brains do very well. Again, it's what allows us to drive. It's what allows us to recognize a stop sign, even if there's a bush growing in front of it. So some of the data, the words or the colors or the shape are obscured by leaves or branches. It's what allows us to identify stop signs if there's snow on it or maybe, graffiti on it. The data that's obscured to a human really doesn't matter that much, but to a computer, it's incredibly detrimental. And then we run into a far, far bigger problem: misleading features. This image here, while perhaps a little silly, is a mission nigh impossible for a computer. The features are simply too similar. Writing an algorithm to identify the difference between the dog and the muffin is very difficult to do. So let's simplify this picture a little bit. On that last image, again, perhaps it was a little silly, but I'm willing to bet everyone watching this now was able to look at it and say, I get it. We've got muffin dog, I understand. And it became very easy to understand. Even here, while I have the labels at the top, you probably didn't read those first. Humans are image-based before we're word-based. So it came up and you said, yep, I see my dogs, I see my cats. And again, you did this in milliseconds, despite the fact that even in this image, the features are incredibly similar. So this leads us to challenge number one when we start talking about the realm of, say, cybersecurity and the current set of machine learning algorithmic tools. When features are too similar, they tend to err on the side of caution. Now, with a cybersecurity tool, you may think to yourself, well, I want them to err on the side of caution. You don't, though, because that creates a huge quantity of false positives. And that's something that every organization is now facing. As we start getting upwards of 350, 400,000 new attacks per day, and organizations are dealing with just an onslaught of events, those false positives become detrimental. They become detrimental to the humans who have to investigate them because it can get very tiring and it can lead to complacency. It's also detrimental to the organization because it starts sucking away ROI. It starts sucking away time from an organization that could be better spent on projects or advancing the company. But believe it or not, this image here is not the biggest challenge of machine learning. This one is. It's when, as I mentioned before with the stop sign scenario, information is withheld, information is hidden. And if we could take a look at all the zero-day campaigns that have been wildly successful in the realm of cyber over the past year, year and a half, even 2 years, all of them utilized this type of technique. They simply used a noisy input to obscure the features that a machine learning algorithm would be processing on. So this is kind of one of the challenges and why machine learning certainly has a place today. It is not going anywhere. It's an incredible technology used in a whole lot of different realms, but it does have its weaknesses and we have to address those. So why do we call these things artificial brains? Well, because they kind of look like artificial brains when you break out, or they kind of look like human brains, I should say, when you break out the math. They operate on neurons, they operate on weights, they perform backpropagation, which is the same thing a human brain does when we reinforce our own learning. And they build connections. As an artificial brain is, I loathe to use the word growing, but as it is being developed, as it is effectively learning and growing, it builds connections and it strengthens some connections more than others based upon its weighting system. But I should note that the math you see in the lower right is not a deep neural network. It is a neural network, but it is not a deep neural network. So what makes a deep neural network? Well, the introduction of hidden layers. Now, hidden layers are kind of the secret sauce, if you will, behind deep learning. The idea is that as inputs come in from any number of sources, it gets processed within these hidden layers. Now you see an example here of 2. There can be many, many, many of them, dozens, if not more. And the idea is that every question as it is developed within the algorithm touches every answer, and to a degree, vice versa. And it allows the strengthening of different connections until the artificial brain develops a solution. Again, the exact same way the human brain works. It's why you can often remember the corner store you used to visit when you were a child and you can't remember what you had for lunch yesterday. You have more connections and a stronger connection between right now and that corner store than you do between right now and that sandwich you may have had yesterday. So those hidden layers are really what make a deep neural network deep, and that's where that terminology comes from. So to kind of give you a quick example, visuals always help people. I like this a little bit because it kind of shows, in a graphical format, of course, an artist rendition, it kind of shows how data moves through a neural network and how it can ultimately get processed with, again, every question touching every answer. And this, I like this graphic because it kind of shows the complexity. Now, this has just a few hidden layers. Again, as I mentioned, they can have dozens and dozens and dozens of them. And the more hidden layers that exist, the stronger it becomes. So what does that mean? What does that allow a computer to do? Well, first and foremost, it allows them to drive. Not a lot of people know what an artificial brain is doing. And again, all self-driving cars are powered by artificial brains. They are unanimously powered by deep learning. But this is important because it shows you what an artificial brain is doing and processing in an artificial car. I apologize, in a self-driving car all the time. It's taking a look at tire spray. It's taking a look at stop signs. It's taking a look at pedestrians, lines. It's processing distances and speeds relative to each other. This is actually something I find fascinating. There are some great examples on YouTube. One of my favorite examples was with one of the most ubiquitous examples of self-driving cars, which is the Tesla. Some people on this call may even have one. There was a great video not that long ago of a Tesla that started braking and started pulling off to the side of the road before, now it was fractions of a second before, but before two vehicles in front of it failed at physics. They collided with one another. And it was already taking evasive maneuvers because it was able to process the conditions and all the relative speeds in relation to each other. And it understood that these vehicles were probably not going to be successful in avoiding one another, so it began to avoid the pending collision. That's what we call predict and prevent. And this is something that Deep Instinct operates on too. That's why we are a prevention first tool. We are not an EDR. We don't detect and respond. We prevent up front. That's neither here nor there. So we'll talk about the self-driving cars again. Now, it's funny, this is the exact same thing your brain does when you are driving. That's why if you've ever wondered why after a 5-6 hour trip, all you've wanted to do is take a nap, this is why. Your brain is processing a tremendous amount of data, and it's doing it very, very, very quickly. And the longer you do it, the more tired you become. A lot of people don't necessarily understand that because you're sitting in a comfy chair. Maybe you've got some iced tea with you or some water. You've got some snacks with you, some good music. Maybe it's a nice day. You've got the window down. You think you're very comfortable, but you're just so tired at the end. And again, this is why. Now, where else is deep learning being applied? Well, you may have seen the news recently. This is an example. It's from a company called myheritage.com, and it's a feature they call deep nostalgia. It is powered by deep learning. And essentially what it allows them to do is you can upload a single photo of an ancestor and it will animate it for you. Now, of course, they will tell you it is an approximation. If you have just a profile of a person, it'll show you what the other side looks like, but it's an approximation. If the person were to have a scar on the other side, of course, it wouldn't put that into the image itself. But this kind of made the news recently because of what deep learning was able to do. Now, several years ago, and even today, you may have heard the term deep fake. This is when you can take thousands and thousands and thousands of images of an individual and you can begin putting them into video, and the computer compensates for lighting, for size, for tone, for direction. With celebrities, that's very easy to do because there are just so many images of them that exist on the internet. My personal favorite was Nicolas Cage being inserted into Raiders of the Lost Ark. That was fun. But to do it off a single picture is really a huge step forward for deep learning. The first one that I saw happen was with the Mona Lisa, and it was fascinating. But these are the types of things, these are the realms that deep learning can take us into because it can simply process at levels that machine learning, human-built machine learning algorithms can't. So I mentioned before that that layers, the hidden layers really matter. So while this looks like it was created in MS Paint, I promise you it wasn't. This is actual output. It's not always pretty, right? So here's our scenario. We've got benign and malicious files. Well, with 3 hidden layers, it's terrible. It's absolutely terrible. It missed a whole bunch of malicious stuff and it classified a whole bunch of benign files as malicious. That's no good. So let's double it. Let's go up to 6 hidden layers. Gets a little better. Still pretty bad though. It created a lot of false positives. It classified, 4 benign files as malicious. And again, it went out and missed a whole bunch of malicious files. But you can start to see towards that upper right quadrant, the first inklings of the artificial brain learning. It was able to effectively reach out, as it were, and grab a malicious file while bypassing the benign one. That's a pretty good step, even right there in the middle of the crosshairs. it successfully avoided a benign file after processing. So we're starting to see the first inklings at 6 hidden layers that it's learning. And then you get to 20, and right around 20 hidden layers, it is now technically perfect. It is computer perfect, as we'll call it. And again, this is what humans do. When you were learning to speak a first or a second language, or third or a fourth, or play a musical instrument, in the beginning, you were terrible. You hit the wrong notes, you said the wrong nouns, the wrong verbs, etc. But as time went on, through exposure and repetition, through constant studying, through constant iterations, you became technically perfect. And you now say the right verbs, the right nouns. You don't hit the wrong notes. And this is again the behavior that data scientists are mimicking as they add hidden layers. So of course, the more layers, the better the accuracy. So why doesn't everyone from Tesla to Deep Instinct and others have a million hidden layers? Processing power, really. It is very computer intensive to create deep neural networks and produce artificial brains. But as that hardware continues to improve, artificial brains will get continually smarter. Now, I do want to make a clarification. We talk about computer perfect, right? But machine learning and deep learning are both probabilistic. They are not deterministic. They are making a confidence level decision. Now, the idea is you want that confidence level in the 99 point and then a floating point of 9's success, but they're always going to have some level of a failure rate. So an example I always like to give is I am not a musician, but if you were to place a musical instrument in front of me with a single piece of music, and you gave me a year, or in my case, probably more, to learn that piece of music, I would become technically perfect at it. I may even be declared the best player in the world of that particular thing, but I'm still not a musician. I simply memorized a data set. If you were to place another piece of music in front of me or another instrument, I'd be back to square one, absolutely terrible. So you can make a computer memorize a data set, and that's easy to do. But then when you train it and it learns a data set, if you keep putting more and different types in front of it, it should be almost as perfect, but it will never be as perfect as a memorized set. So again, the idea is while there's always going to be failure rates associated with machine learning and deep learning, the idea is to have those failure rates so impossibly small that they would never occur in a human lifespan, or preferably many human lifespans. So that's an important distinction to make. These are not deterministic. These are not signatures. These are not reputation. They are making decisions based upon a confidence level. So I do like me some XKCD, but I want to talk about noise a little more. Now, we saw noise earlier, a silly example with cats wearing glasses and dogs with hats on them. But here's a real life example where they ran an image on the left-hand side there of a panda through a machine learning model. And it said it was 57.7% confident that it was a panda. Now, that's pretty good. It got it right, and it was very good. But then they introduced a variance, a very small variance, I should add. And suddenly, when they introduced the variance, the machine learning algorithm ran, and it came out, and it was 8.2% that it was a nematode, which is a kind of a clear little worm. Now, 8.2% confident, not very confident. So it didn't really know what it was dealing with there. But of course, it was just noise, so it wasn't an animal that it was processing. But when that very small variance was placed together with the primary image, it was now 99.3% confident that it was a gibbon, which of course is a monkey, an ape, one of the two. Now, of course, that's terrible. That's a huge error miss. So this is what we talk about when we talk about inserting noise into a data set or into an event. So this is an image, not really that impactful in the world, although I guess if you have a self-driving car, this can be very concerning. But what does it look like in the cyber world? Well, here's another example. And we have here a piece of malware. And when you were able to run it through a feature extraction model, you could find the features that make that thing a malware. And this particular one had 491 features associated with it when it was generated. But what the threat actors did is they inserted 2 perfectly benign, perfectly normal API calls into the binary, which ultimately layered and obscured the features that make it malware. The end result is that when it reached the machine learning algorithm, it didn't have enough feature set to see that it was malicious. The end result was that it got classified as benign and it successfully compromised the company. This is a real example from a manufacturer that was compromised. So this is a challenge. This is one of the reasons that machine learning has begun to struggle. And I do say it's begun to struggle because it is still a phenomenal tool and it will be for some time. But threat actors, they've gotten wise. They know exactly what they're doing now when it comes to defeating this type of technology. Now, it certainly isn't easy to do by any stretch of the imagination. Please don't think that there are people just sitting around in their offices or in their basements and just casually defeating machine learning algorithms. They are not. But at least yet. But at a state sponsor level, at an advanced threat actor level, absolutely. And again, we don't have to, you don't have to take my word for it. Simply going out to any of the blogs that track threats throughout 2020 and even into 2021 so far, you'll see that some of the strongest tools that were regarded as the best in the world just a handful of years ago have begun to struggle because new tricks and techniques have started to arise that allows machine learning to be defeated. So again, I want to talk about just a quick recap, if you will. The challenge of machine learning algorithms, while they are absolutely fantastic, is always going to be that second step. The fact that at some point a human or a human-derived automation tool is going to be performing feature extraction. They're going to teach an algorithm what a thing is from a human's perspective. Now, that of course arises that, that ever so challenging challenge, which is the unknown unknown. We can only design algorithms for that which we understand, for that which we already know. Deep learning simply doesn't have that problem. Deep learning consumes raw data. Again, just like you learned what a dog and a cat were. It consumes raw data and it processes it through a series of hidden layers until it develops an understanding, which in many cases can be far deeper than what a human can do. And we see this throughout the medical field. We see this throughout the game industry, where deep learning has simply exceeded human capability. Now, of course, we all know that chess was solved by computers a long time ago. I'm using the word solved incorrectly as though technically chess has not been solved, but no human can defeat a computer. That's a fair statement. But when we start to teach computers how to play the Chinese game of Go, they were pretty bad. Even the strongest computers on Earth really struggled with playing the game Go, even though a far simpler game in terms of moves or in terms of how it is played, the strategy and the possibilities behind it are far greater than that of chess. So Google said that was unacceptable and decided to build an artificial brain to play Go. In just 7 months of training, it proceeded to take on the strongest Go players in the world, and it defeated them all. Something data scientists didn't think was going to happen for another decade. And while that in and of itself is a fascinating story, I'm actually more interested in what happened shortly afterwards. Google took that exact same artificial brain and pointed it at the game of chess. And they said, okay, these are the rules of chess, now go learn. And it played itself in chess, millions and millions and millions of iterations, but they only let it train for 4 hours. That was it, just 4 hours they let it train, possibly 5, but I think 4 hours. Where it then proceeded to take on the #1 chess playing computer in the world, at the time a computer called Stackfish 8. Stackfish has had more iterations since then, but at the time it was Stackfish 8. And the deep learning model did not lose a single game. Now they tied the vast majority, but the deep learning model did proceed to beat it, I believe 27 times. So that's, again, an example of the fact that deep learning can understand a problem and a challenge at a level that no human simply could. And I definitely don't want anyone to think that this is some mystical thing that Deep Instinct is doing or that it's in labs somewhere. It is not a science experiment. Deep learning is currently all around us and has been for the past 10 years. In systems you use every single day, from, again, Netflix and YouTube, which of course probably everyone uses, one of the two every single day, but to logistical systems, natural language programming, speech recognition, all of these things are being powered by deep learning. And we're happy to insert ourselves into that list as well. But it should also be pointed out that when we start talking about deep learning, even there, not all systems are created equal. Right now, the conversation is machine learning v deep learning, or machine learning, as I like to say, and deep learning. But even within deep learning, not all systems are created equal. For example, you can't take an open source framework like TensorFlow, which is the most popular, I believe, right now, created by Google. Anyone can go download it and use it. And you can't make it work for cybersecurity. Now you can try. We tried. And there are other security companies right now that are trying, but it wasn't built for that. And there are things you can do with images like remove data and still understand what the image is. You can resize images and still understand what the image is. You can't do that with base binaries. I can't arbitrarily decide that a PDF file is a executable as an exe, right? I can't arbitrarily decide that a 1 gig file is a 1 meg file. I can't make those decisions with binaries. So it needs a completely different framework, which we then built custom. So we are the only company in the world that has a framework designed for cybersecurity. And that's important because there were only 5 frameworks in the world when we decided to build our own. It's very challenging to do. It takes a lot of time, effort, money, and resources. But we were the recognized 6th framework in the world. I believe we're up to 7 now. So it's certainly growing. It's going to be much more pervasive over the next 10 years. But it's important to have this knowledge early so that whether it's cybersecurity companies or any other company is saying they're powered by AI. Well, what does it mean? They're powered by deep learning. Well, what kind of framework are you using? Is it Caffe? Is it TensorFlow? Is it PyTorch? Is it your own custom built one? And if it's custom built, how is it built? These are the questions we have to start asking vendors and really any type of technologist, so we can better understand what's going to protect our environment or what is protecting our environment, but also what we may want to move to. And that's something I always like to talk about too, because right now, signature heuristic and machine learning is all around us. And a lot of times I talk to companies and they say, yep, we just had a breach and we're looking at these vendors over here because this vendor let us down. And I always scratch my head and say, let's forget about vendor name. Let's forget about logos. Let's forget about all that. Let's realize that a signature heuristic machine learning technology failed you. And you're looking at a signature heuristic machine learning technology to protect you, or you're looking to move to that. Maybe it's time we start looking at fundamentally different types of technology if we're going to kind of move forward into the 2020s and start protecting against advanced threat researcher or threat actors, as well as AI created malware, which we are starting to see. What was theoretical just 2 years ago is now fairly pervasive in the industry. So I really want to thank everyone's attendance today. This was an excellent platform. I hope you enjoyed the webinar. And of course, if you have any questions at all, please feel free to use the Q&A button and I'll answer them to the best of my abilities. Now, there we go. No questions. I'll take that though. Here's a good one. Do I have any suggestions for a deep learning home lab? Oh, absolutely. I also want to build a deep learning home lab. Right now, my recommendation is to use TensorFlow. It is free. Anyone can go download it. The source and information is up on GitHub. I've downloaded it. It seemed to, it works well, of course, as long as you're using it for the right thing. I tried to use it to predict lottery numbers, didn't work. No, I'm kidding, of course. But I recommend TensorFlow, although while I have not used it myself, PyTorch is an outstanding framework that is starting to gain a tremendous amount of traction. And if someone were to tell me that in a few years, PyTorch would even overtake TensorFlow in terms of downloads and utilization, I would believe it, simply because it's an absolutely stellar framework. I will say this, a home computer struggles to train artificial brains. Artificial brains are really a process of GPUs and RAM. So while a lot of computers, most computers have 1 GPU and some of your more powerful gaming computers have 2, and they themselves have multi-core. When we start talking about deep learning frameworks, we're talking about hundreds of GPUs, all daisy chained together. So you can absolutely build your own home lab. I wouldn't expect to get the same results as, say, some of the larger labs like a Deep Instinct or a Tesla or a Google might have at their advantage. Has this been recorded? Yes, it has. I believe that we will be able to get that information afterwards. So definitely. Do you have any signal? Do you see AI? Okay. Do you see AI following a similar path to semiconductors and more law? I absolutely do. What a great question. Yes. So we have already seen it. My favorite example, again, going back to Google, they've got a great lab within within Google called DeepMind. I remember when then CEO stood in front of about 5,000 Google employees and made the very bold claim, and it was recorded, which is, why are humans still driving cars? Computer do it so much better. And I believe he made the statement in 2010 or 2011. 5,000 people laughed. The internet proceeded to laugh afterwards because what a silly statement to make. And the laughter didn't die down when the first Google cars started to make their way onto YouTube, and people saw that they struggled to go around a circular track, and they didn't know the difference between a stop sign and a yield sign. Today, self-driving cars are in almost, or self-driving vehicles, I should say, are in almost every factory in the world, and self-driving cars are successfully navigating LA traffic. They're only going to get smarter. And of course, my personal prediction, so please grain of salt with this one, but by 2040 and maybe even 50, we're going to see quantum computing becoming much more common, I think, even if it's at the industrial level. Quantum computing paired with advanced deep learning is going to give rise to some incredible solutions to problems that humanity has struggled with for a very long time. So I'm very optimistic. Where does unsupervised ML fit into this? Oh, great question. So I like that you mentioned unsupervised MLDL because that kind of goes along with supervised as well. Now, Deep Instinct, we use supervised data. What that means is we know what the data sets are when we are feeding it into the deep neural network. So we know what the expected output is. Therefore, if it's wrong, we can go in, make little tweaks to the weights and to the backpropagation testing methodology to get the right answer. Once we get the right answer, we can then throw that data set away, bring in a whole new data set, and hopefully achieve high results and let the real training begin. Unsupervised training, however, whether it's machine learning or deep learning, is just that. It basically learns effectively on its own from data that even the human isn't necessarily aware of. There are some really cool examples of this happening. Some of my personal favorite ones were some scientists in a lab were training a robot to avoid obstacles and move from one side of the room to the other. So of course it had a series of cameras around it. And when they were just taking a look at how the algorithm was forming, they discovered a neuron that they didn't quite understand why it was there. And it turns out that the computer effectively taught itself image recognition. It was watching the scientist watch it. Sounds creepy, but of course it's fascinating. And that's a good example of unsupervised learning. It wasn't programmed to do that. It simply took in that data. Now, it was terrible at it, and it couldn't get enough data to become good at it. But I do find unsupervised learning really fascinating, but algorithmic models aren't quite there yet to make it as strong as it needs to be. So supervised learning will probably still be the norm for quite some time. Could you please one more time differentiate between AI, ML, and deep learning with some real life examples? Certainly. So again, AI thinks signatures. Signature-based systems are effectively AI. Anytime a computer is making a binary decision on its own based upon information it has, that could be classified simply as artificial intelligence. It's stimulus response. It sees something, it understands what to do with it, and it makes the correct decision. So that's a general AI term. Machine learning is, think of it like human algorithmic driven. So a human sits down and says, I'm going to write an algorithm so that a computer understands something moving forward, even if I can't explain it exactly. Great example of that is your Microsoft Surface or your Apple iPad. When you take that pen off and you go to write on that particular tool, you may rest your palm on the screen. Now, it's designed to respond to touch. So why doesn't it respond to your palm? Why can you rest your palm on the screen and still write with the pen? That is a machine learning algorithm. You wouldn't want to train an artificial brain to study tens or hundreds of millions of people resting their palm on a screen in order to build an artificial brain. Heck no, it's easier to do that with a machine learning derived algorithm. You simply explain the features of a palm. You explain to a computer the conditions under which you do not want it to register that palm. Maybe the Bluetooth is engaged with the pen, or you're in an app that allows for writing, etc. And then you can just let it go. So that's a great example of machine learning. And those are the problems that machine learning not only solves now, but will continue to solve far into the future. Deep learning, the best example, the self-driving car. All self-driving cars are powered by deep learning, and that is what's going to get us to full self-driving cars, the ability to simply get in, announce your destination, and it will drive there. So those are kind of the three examples I like to give: signature-based cybersecurity, tablets when you rest your hands on them, and then of course the ability for cars to identify the world around them. Can you please spell the name of the tool you mentioned? Absolutely. Which tool? So let's go through some of the ones I may have mentioned. So PyTorch, one of the frameworks, that's PY is in Python, TORCH, PyTorch. Then of course there's TensorFlow, Tensor, TENSOR, and then Flow, FLOW. That one is created by Google, so that should be pretty easy to well, Google. And then some other tools, of course, Deep Instinct, it's hard to beat that one. That's me, that's this company. But of course, if you need clarification on some other tools, I'd be happy to kind of circle back around on that. So hidden layers, yes, this is kind of the challenge. So you'll notice I may have struggled to pick my words throughout the presentation at times because I loathe to use the term black box or magic or anything like that. That is not what this is. This is science. This is math. With that said, hidden layers are where the magic happens, I say reluctantly. And the reason I say that is because as those hidden layers exist within the algorithm, that is where the data is being passed to, and then that data is touching every other point within the hidden layer. It's getting feedback, and then that is touching every other point within the hidden layer. And all of that begins to kind of conglomerate into a final output answer. Now, how it does that, that's actually a bit of a mystery. And I don't like to say that because, again, it gives deep learning this air of, magic somewhere, and it's not. But one of the dirty secrets of deep learning, if there is one, is that you will never hear a data scientist, or I should say you will rarely hear a data scientist say, my artificial brain is failing. I'm going to go figure out why. No, they simply say, my artificial brain is failing. I'm going to go build a new one. And again, the reason for that is because if humans could build an artificial brain from scratch, we wouldn't need to train one. We would just build one from scratch, much like we do machine learning algorithms. So the idea is a deep learning model learns its world with its parameters as set forth by the human. It learns its world in ways that we simply could not understand. And that's why it's so successful at playing chess, playing Go, flying planes, driving cars, or discovering new advancements in the medical field, which it is doing, which deep learning models are doing all the time. Really great papers published on that. How does Deep Instinct address adversarial attacks that could defeat the AI's classification? Man, what a tough question. Good question, tough question. So adversarial attacks are the bane of cybersecurity. We take it very seriously. We are in a constant state of trying to strengthen our capability to both identify and counter a successful adversarial attack. The most effective way to defeat deep learning is to poison the well, as it were, is to poison the data that a model learns on. We've actually seen this, and I'd love to say we saw it last month, but the truth is we saw it about 3 years ago. So state-sponsored threat actors, with all the resources of a government behind them, they have incredible capabilities. So the end result is that they are trying to poison the data sources that supervised learning relies on. So how do you get around that? Well, you verify your data source constantly. You also use many data sources. You don't just pull from VirusTotal. You don't just drive your car around a single track. You get it out into the world. You pull from dozens and dozens of different sources on an attempt to make sure that if you start seeing a deviation, you can identify if something has been poisoned or tampered with. It is challenging, and of course, that is going to be the cat and mouse game that we're going to see for the next 1, 2, maybe even 3 decades. The adversarial networks, or generative adversarial networks, or GANs, taking on deep learning models. Yes, correct. AlphaGo did lose 1 game to the South Korean World Championship. That is true. So they played, I believe, 5 games, and I believe the AlphaGo won 4 of them. So you are absolutely correct. It was more successful when it got turned on the game of chess, but you're right. It did not sweep the human champion. However, I am sad to report that the South Korean champion did retire shortly after his loss, stating that computers had effectively not made the game fun anymore. So that's unfortunate. He was a great champion. But since then, AlphaGo has gotten much stronger, and we're starting to see it kind of pull away. Of course, it lost that one game a few years ago now, and the latest iterations of AlphaGo and AlphaZero are continuing their advancement. I can also report that machine learning has reclaimed the crown in chess. I believe, please don't quote me on this, but I think we're up to Stackfish 12 at this point, and it has reclaimed the crown. Though I will say this, the artificial brain has kind of stopped playing chess, and it hasn't spent time studying. So we'll have to see if someone wants to take up the mantle and take on the latest Stackfish version. I want to continue with that question as well. Successful decisions need to come through unsupervised learning less. Yes. So the question is, since this is a probability-based decision-making, does training AI on low probability but successful decisions need to come through unsupervised learning, since it's less ROI than human supervised learning to build an environment? Such a challenging question. I don't feel necessarily qualified to answer that one. I am not a data scientist. But with that said, we're going to have to kind of see how this realm plays out in the realm, in the examples that you gave there on, again, low probability, unsupervised learning. You can start getting binary outcomes from deep learning. I don't know if it's the most efficient use of that particular technology. Again, I feel that's a problem that machine learning solves in a much more efficient and quicker matter, but it's certainly not outside the realm of deep learning, and we may see data scientists start going down that route. What was that paper you were referring to? Shoot, I got to write down my stuff. I will have to, I apologize, I do. I will have to take a look at the video and I can get you that information. Do you foresee DevOps becoming more ingrained with ML? Yes, absolutely. Definitely. MLDL, DevOps are going to become an integral part of delivering this technology, because one thing that I always like to talk about is having an artificial brain in and of itself is kind of academic. It doesn't do anything. It needs to be placed in some kind of a vehicle. And the example I always love to give is, you can have the best engine in the world, but if it's sitting on a showroom floor and not in a vehicle, it's not doing much for you. Or if it's not in a factory, it's not doing much for you. It needs to be in an engine. So DevOps in the future, my belief is that we're going to start seeing solutions wrapped around, or rather solutions delivered by DevOps wrapped around ML and DL solutions. Can you fix problems in data? Yes. I don't know. I said that very confidently, but the truth is, I don't know if that's something that can be accomplished with this particular type of technology. I want to say yes, because what can't deep learning do? But the truth is, we'd have to talk about the corruption level or the missing aspect of that data to see if that's within the realm of deep learning itself. Why does TensorFlow and most of the others state on their home pages to use machine learning and not deep learning? As this actually is, makes it confusing. Oh, it does. It really does. So it really comes down to processing on raw data. And that is going to kind of be the key moving forward, and the word you have to listen for moving forward. So an example I'm going to give is within the cyber realm. There is another company out there that is utilizing deep learning for cybersecurity, but they're doing it in a very curious way because they are using TensorFlow. But didn't I say earlier that TensorFlow really isn't very good at this? Well, it's not. And what they're doing is they're actually doing feature extraction. They're doing machine learning feature extraction on the data, and then they're feeding that into the deep neural network. It's a little confusing to me because essentially they're letting their deep neural network only learn that which they've pre-identified as a feature, instead of letting it learn on the raw data. The challenge that we see with something like PyTorch or TensorFlow, which are open source, is that they're base frameworks and they can be utilized for pretty much everything, but they're not designed for everything. So a lot of times, depending on how you apply TensorFlow or PyTorch or Caffe or any of the other ones, you may have to perform some level of machine learning feature extraction before it can be fed into the framework, because the framework itself isn't designed to understand everything. So that's kind of probably why they're saying that. In fact, not probably, that is why they are saying that, because they understand that for their framework to effectively learn and effectively work, sometimes it needs to have the feature extracted data first. Now, of course, if you were to say build an image recognition system, you wouldn't need to perform that level of feature extraction with TensorFlow. That's what it's designed for. You can just feed images into it with raw data. So it can be confusing because there's so few frameworks out there right now, and everyone's trying to kind of back end their solutions and their models into these very few frameworks. And building new ones can be very challenging. Phew. Okay, so that was all the questions that came through. Of course, my contact information is available. The recording will be available. So if there are any other questions that anyone has, please feel free to reach out to myself or CSA, and we can go ahead and get all of those answered for you. But I definitely I appreciate everyone attending this webinar. It's a lot of fun. Matthew, back to you.
Well, Brian, I just want to say thank you very much. I thought that was great. That was a terrific introduction to the topic, and I don't know about everybody else, but I'm certainly going to want to learn more from that. Great. Well, thank you, everybody. And if you have any questions, please feel free to follow up either with CSA-DC or with Brian directly. Have a great afternoon.